Hello and welcome to our presentation. We're team number 1 and today we will be presenting our project, which involves building a bare metal operating system that includes a command line interface, multimedia display functionality, and a game. Before we dive into the detail, let's introduce our team members. I'm Thao Chin and I work on display an image of the team and display text over images and game mechanics. Our project was divided into 3 tasks. One is implementing a welcome message and command line interface, CLI. Second one is enabling image, video, and text display. Third one is developing a basic game that integrates with the CLI. Our first task was to create a command line interface, CLI, and a welcome message for our bare metal OS. Let's boot this up. As you can see, when the OS boots, we display a ASCII art welcome message. We use the UART to capture user input and implement a functional CLI. In the CLI, user can enter command like help to display available commands. Now we're going to display the image. We can offset it, go up, go down, go left, go right, and then we'll display the video. Now we're gonna start the game. Hit space to start. You can shoot the ball. When three or more balls have the same color, they will explode. You see the score is being recorded. When the ball have reached overflow the row, then the game is over. As you can see, demonstrating this way, there's a delay in the Raspberry Pi sending the signal to display it. So for to check the video, we will use Kimu to demonstrate in detail on our project.
Hello everyone, my name is Ho Wen-Hui. My SID is a 3924729, and today I'm responsible for demonstrating the CLI implementation for our team. So first, when the CLI is initiated, it displays the prompt. It's displayed the prompt Group 1 OS. This is where user can input the commands, and the input is stored in a buffer called CLI buffer, CLI buffer, which has the max command size is 10 that we have defined at the top of our file, which is 100 characters long. As you type, each character is echoed back to the console and giving the real-time feedback for the user. And the next part is the backspace and delete handling. I can show you, this is the section so that we can handle the backspace and delete. Since we have added the support for the backspace and delete operations, when the user presses the backspace or delete key, the CLI will erase the last characters. So let me make the file. For example, when I type something, I can use the backspace to delete the last character in the array, in the string. And the next one is the section for handling the history command. The CLI maintains a history of up to 10 commands that we can navigate through previous commands using the plus key or move backward and to move backward, and the minus key to move forward. This is especially helpful when re-entering or modifying the past commands so that we can save time and effort. Like for example, when I type 1, 2, 3, 4, I type plus to go up from 4 to 1 here, and I type minus to go from 1 to 4. Especially, we have included a clear line that we included in menu.c file that I have included over here, so that I have included a clear line so that when we type minus or plus key, it will keep the prompt in the same line and it will never move to the next line. So that's my history navigation handling. And the next one is the tab completion. As the user types a command, they can press the tab key to automatically complete the command based on what's already in the buffer. So if there are multiple possible completions, the CLI will list them and allowing the user to choose the correct one. We have even extended this to handle the help commands specifically, and the user can easily find the assistance with any command by typing help followed by a partial command name. For example, let me do a command. First start when we type S, it will show up the possible matches like show info or stop it. So let me do a little bit different. When I type tab, it will complete the show info for me, and I type enter. Yep, it will execute the function. And about the help command with the partial command name. For example, when I type help and I use tab, it will show off the possible matches that I have included in the program. And there is 12 commands that I can use. For example, I can type B, it will show me the baud rate. And this is the format that we have included as a table so that it can show the command number, command name, and the usage. For example, baud rate, the common number is 4, and its usage is to set the value for the baud rate. For example, baud rate, let me set it to 1900. Successfully set it, and when I check here again, we can see the possible matches. In this case, I will choose baud rate, and currently the baud rate has been set to 1900. And the last one is the command execution. Here is the command execution handling. Once a command is fully entered, the user presses enter and the command gets processed. The CLI then checks if the command is valid. And here is the list of commands that the CLI will go to check. Like for example, some commands like help, clear, or game, and show info trigger the specific functions. And if there's a invalid comment, the CLI program will prompt a error message, guiding the user to type help for a list of valid comments. So let me type 80. So it will alert a invalid comment message and ask the user to type help or help command name for the valid comments. So let me type help. Here is the acceptable comments menu for the CLI and the whole program. At the bottom one, there is also an instruction so that the user can follow to see what is the detailed information of the commands. For example, let's follow by help and command name. I will type help and display image here. Corresponding to the command menu table, the display image number is 8 and the usage is to display the team image. And the last one is the exit command. We have the exit command, which is really, let me go to the exit command. And this one is the very useful command to shut down the system. It holds the OS and waits for a manual restart. And you will see the prompt telling user to press Control C to return to the terminal. So let me type exit, and I will try with the tab completion here. And shutting down at this time, I cannot type anything, but the instruction asked me to press Ctrl C to return to the terminal. So let's Ctrl C. And at this time, when I want to go back to the program, I will have to make again. And yeah, that's also the end of the CLI demonstration.
To display a background image on the screen, we convert an image into our ARGB32 data using an online tool called Image2 CBP, recommended by the professor, and then render it using our custom function called drawImage. This is our drawImage function, image where you initialize where the start X and start Y is, then the data of the background or the image. This is the data that I have converted from the image using the tool, and then the image width and its height. In this function, it used a function draw pixel argb32 to draw each pixel in the picture. So it go through. It start from the start Y and start X. Then we'll print out the data from the data array of the image. Then over the background, let me show you the image. As you can see, there are text over the background, and we use custom fonts to display the name of our team members in different colors. As you can see, we use a function called drawString, where it would take in the start X and start Y to start the string, and the color of the string and the scale of the words. So it will use the function draw character, which it will draw each character in the string. For the start character, it will know where the character position is. Then take in the character input, the color, and the scale. For our scale, we set it to be each character is 8 pixel, and type for the scale is how big the character gonna be. Then for the font, we are using custom font that generate from a bitmaps like this. This character is a 8 times 16 bitmaps. This is example of letter A, and we're taking the data array for a SCII character from the character 32 to 126. So in this function, it's checking if it's within this range, then they would know which character are they taking in and print it out. The text is rendered using pixel data for each character, which we map manually into a bitmap format. We use the drawChar and the drawString function to display the text on the screen.
Hi, my name is Nan, and I will instruct a frame buffer manipulation and game features. I will explain the video display functionality we have developed. The video playback process is very similar to displaying a static image. However, instead of just one image, we display a series of frames consecutively. We began to extracting the video frame into arrays, like this one, and this is the file is quite heavy, so it cannot load. But this is the array, and this is the header for storing the length and the index of the frame array. Once the command to play the video is selected, play video, the program sequentially load and display this frame. There are three main files involved in video playback. The first of all is the frame buffer.c, the second one is the draw.c, and the third one is the video.c. The frame buffer.c and draw.c file manage screen setting and drawing function, including the core function like draw image video, which is responsible for rendering each frame. This function loops through the pixel data and draw it on the screen using the draw pixel argb32. The video.c is where the video logic plays. The function play video used a loop to display each frame. On the screen to ensure smooth playback by working with wait millisecond. This one will place in the interrupt.c. This function controls the delay between frame pausing execution for about 100 milliseconds. Now I'm gonna display the video. As you can see on the screen, the video is on the right, and on the left in the terminal. For each frame when being displayed, I have inserted the UART deck I for showing each frame is displaying. For stop play and able to enter another command, we will press X.
All right, so hello, Dr. Ling and everyone. My name is Sung, and today I will be showcasing the game of our final group project for embedded system and operating system. So now let's get into the game introduction a little bit. So an overview of our game is that it's basically a bubble shooter where the player controls a shooter at the end and tries to shoot the balls to make them explode before they reach the bottom. And throughout the game, there will be an increase in difficulties as the score goes up. So these difficulties affect the speed of which the ball falls down. So now let's get into the demonstration. Here in the COI, I will type game. And here the user is prompted to hit space to start the game, or hit Q to quit, or P to pause. So now let's start. So here you can see we control the shooter, and then we can shoot, and then they explode the balls. So basically the score is calculated by 10 times the balls that are exploded. And now I will try to pause the game. Here is the pause menu. And here the user is also prompted to continue the game, quit, or reset the game. So I'll continue the game and try to lose here. I'm trying to lose as quick as I can. And here is our game over screen. So as you can see in the COI, they are prompted that the game is over. There are no more spaces, and they can press game to play a game. So I would love to play a game here. And here now I'll try to showcase the difficulty. So as you can see right now, the player level is level 1, and as I go over 150, it will proceed to go to level 2. And I believe that level 3 is 300. So let's try to see if we can reach that here. And I believe we can if we make the right choices. All right, here. And yep, and when level 3 is reached, the speed of the ball drastically increase, as you can see. And now I just lost again. So basically that is the score and difficulties session of our game. And now I will go over the code. So basically, let me move this here. So basically, the game goes into the game.c file, and here it is going to go into displaying the welcome screen here. And in the welcome screen, the move shooter will be called, which is responsible for pretty much everything related to shooting your ball, as well as like moving the shooter around. So talking about ball, the balls.c here is responsible for the matrix as well as the logic behind every balls. And there are also many other files that are utilities, such as like the background of the game, the game intro, the game over screen, the game welcome screen, as well as interrupts provided by the doctor of our class, as well as other functions from the kernel.c folder, which is from frame buffer or draw.c and draw.h. So that is basically it for our game demonstration, and thank you for listening. See you.